Hello, this is the content checkpoint assignment for the circular motion unit. To start off with any of these content checkpoints in reviewing for the test, the first thing I do is recommend that you read through this list of key ideas and skills, because you're basically going to be using these throughout on all of the different questions. And so making sure that you have a good foundational understanding of these ideas will help you throughout the assignment. If you haven't already watched the video that I posted for the extra practice with circular motion worksheet, I recommend that you go back and watch that, because there are a lot of good concepts on there that will help to reinforce what you see in this video. So really, in preparing for the exam, I recommend that you watch both of these videos. So section A is just going to cover some concepts. The first one here says a car travels around a circular racetrack at a constant 150 miles per hour. Does this car have constant speed, constant velocity? Is it accelerating? Well, the 150 miles per hour is its speed, all right? It's going to be going 150 miles per hour. In terms of its velocity, because it's changing direction, it's going to be changing its velocity, all right? So constant speed, but the velocity is not constant because it's changing direction. And then if the velocity is changing, by definition, it's going to be accelerating, because acceleration is a change in velocity over a period of time. And so all of it's constant, and this is the speed. We've got constant speed. The velocity is changing. Since the velocity is changing, it's accelerating. Going on to part 2 of this question, it asks to make a force diagram for the forces on this car. It's turning left around the racetrack, so that's important to realize when we're looking at the back of the car. And this is make sure to include the on-by and the types of forces. So for this one, we've got a gravitational force down, Fg, which is on the car by the Earth. We've got a normal force, which is upward on the car by the road. And then it's important to remember here that the force that keeps a car moving in a circle when it's traveling in a circle, the force that helps it turn, is a frictional force. So we've got an FFR here, a frictional force, which is on the car by the road. One last thing, we know that the gravitational force and the normal force are the same because it's not accelerating in the upward or downward direction. It's just accelerating to the left. All right, which brings us to question number 3. It says, according to your FBD from question 2, in what direction is the car accelerating? It's accelerating here, to the left. Question 4 asks us to look at an airplane that is traveling at a constant speed. It says that first that it wants to draw acceleration vectors for each of 5 positions shown. Okay, and then it says when the plane is at the top of the loop, all right, draw an FBD for the forces acting on the plane. Keep in mind that the direction of the lift force relative to the position of the wings. So in this one, we've got here a plane. In the first part of its motion and in the last part of its motion, it's traveling in a straight line. And if it's traveling in a straight line at constant speed, it's actually not accelerating in either of these 2 locations. Now, in the period where it's going around the circle, it's always accelerating towards the center of the circle. So we've got an acceleration vector there, and down, and over this way. Okay, so that acceleration is always going toward the center of the circle. Now for the FBD, there are a few things here. First of all, gravity is pointing down. We're looking at that plane that's at the top position here, by the way. So Fg is going downward. And also, normally on planes, there's a lift force, which helps to lift the plane upward. But in this case, because the plane is upside down, that lift force, which comes from the curvature of the wings, ends up pushing the plane down. And then lastly, if you think about it here, it's going to the right. There's some sort of propulsion force probably pushing it forward. All right, and there's an air resistance force pushing it back. All right. And those two are going to be constant because we know it's accelerating in the downward direction. And those are all the forces on here. So air resistance back, applied force, propulsion force forward, gravity down, and then the lift force is kind of weird. It's upside down in this case, so it's going down as well. You could have left off the propulsion and the air resistance force in this one and just had the two downward forces. I think that that would have made sense as well. But as it's an airplane and it's going pretty fast, it probably would have air resistance and something continuing to push it forward. For question number 5 and 6, actually, we need to be taking into account the different proportionality relationships that we have. So for problem number 5, you have to look at it, and it says that we've got a radius doubling here. So if you then remember that the centripetal force is proportional to 1 over the radius, or it's inversely proportional to the radius, if you double the radius, you cut the centripetal force in half. You're doing the opposite, you're doing the inverse. So doubling the radius means the centripetal force is cut in half. So we have 10 divided by 2, which ends up equaling 5 newtons. For problem number 6, it works a similar way, except it says in addition to the radius of the path being doubled, also the speed is doubled, and you have to think about what effect that has on the force. So we've got Fc is proportional to 1 over r coming into play, but also centripetal force is also proportional to the speed squared. And so if we think about this, the effect of doubling the radius we've already seen cuts it in half. But the effect of doubling the speed, if you remember, is quadrupling the force. All right, so what we've got here is we've got 10 newtons. All right, and then we're dividing it by 2 because of the radius. And then we have to quadruple it or multiply it by 4, all right, because of the change in speed. And what you end up with there then is 20 newtons. Number 7 is a little bit tricky. So number 7 actually takes into account the same two proportionalities that we were looking at for number 6. It says there's a flea on a record player which rotates 30 times in 1 minute. It says the flea walks from the middle of the record to the outside. Does the force get larger, smaller, or stay the same? So in this case, you have to think about what would be changing as the flea walks towards the outside of the record. The radius is getting larger. That's one thing. All right? So radius is going up, okay, which means that the centripetal force would go down because of the inverse relationship. However, there's more to it than this, because as it approaches the outside, what's happening is it takes 1/30th, well, I guess it says it's going around 30 times in 1 minute, right? So it takes 2 seconds for the record to spin around once. And it doesn't matter if you're on the inside of the circle or the outside of the circle, it still takes 2 seconds for it to spin around once. However, on the outside of the record, the circumference is larger. So it's moving a little bit faster on the outside. It has to go all the way around the entire outside in 2 seconds, rather than going around a smaller circle on the inside. So what we see here is as the flea walks toward the center, toward the outside of the circle rather, the speed is increasing as it walks towards the outside. And if the speed is increasing, then we know that the centripetal force is increasing. And in fact, that speed, because it's squared in the proportionality, that speed ends up having more impact on it than the radius does. And so what ends up happening here then is that force is going to end up increasing. Okay, because even though the increased radius would decrease the force, having that increased speed as well ends up overwhelming that effect, and we end up having an increased force overall. Okay, for problem number 1 here, I've given you some information, and I asked for the force of tension in the rope. Really, this is just using the basic centripetal force equation. We have to figure out, though, the speed before we can do that. So it says the period is 0.2 seconds on this. So to find the speed then, we know it goes around once for the whole circle in 0.2 seconds. So we know 2 pi r is the distance all the way around divided by the amount of time it takes. All right. So that 2 pi r here is 2 times pi times the radius, which is 2 again, divided by 0.2. All right. And when you calculate that, you end up with a speed of 62.8 meters per second. All right, so that gives you the speed. Just distance over time. It goes around the circle one time in 0.2 seconds. So that's how that works. All right, now centripetal force is going to equal the mass times the speed squared divided by the radius, which in this case equals 0.5 kilograms. Actually, I normally don't include units in here. I think that gets confusing. So just 0.5 times the speed squared, 62.8 squared divided by the radius, well, that's 2, sorry. And if you calculate that, you end up with 987 newtons. All right. That is the value of our centripetal force, which is also just the tension force in this case, because the tension force is the only force acting in the circle. All right, for number 2 here, we've got a car going around a roundabout on an icy day, and it says the maximum friction force coming from the road is 2,800 newtons. And I ask, what is the fastest that the car can go without sliding? So on this one, again, we have to think about an FBD. If we're looking at it from above, we're going to ignore gravity, which goes into the page, and we're also going to ignore a normal force that comes out of the page. And so really at this point, all we've got is a friction force, all right, pushing it toward the center of the circle. That friction force equals 2,800 newtons, we know. All right, and so that friction force really, in this case, is the centripetal force. And again, we're looking at Fc equals ms squared over r. Okay, so we know 2,800 equals 1,000 times s squared over the radius, which in this case is 10 meters. Right. If we simplify some of this, we end up with 28 equal to s squared. All right, so the speed here in this case would have to be 5.29 meters per second, the square root of 28. If you went any faster than this, your car would slide. If you went slower than this, then friction could keep you moving in the circle. Okay, for problem number 3, we've got a wagon going over a circular hill, it says, with a radius of 20 meters. And I want to know the fastest the wagon can go without losing contact at the top of the hill. Now, there's a little bit of a hint here. It says if you're about to lose contact, right? So when that wagon is on the top of the hill, there's an FG going down and there's an FN going up. If the wagon were just stopped at the top of the hill, those would be equal. However, as you go faster, a larger downward force is required to keep you moving in the circle. And so, generally speaking, we have less and less normal force as you're going faster because there needs to be a larger downward unbalanced force to keep you going in the circle as you get faster and faster. And so when you get really, really fast, this is shrinking down and down and down. We end up right before you lose contact with the hill having no normal force on there at all. And so there's just a gravitational force. Okay, the gravitational force is 2,500 newtons. We know there's no normal force here. You're just about to lose contact. You're going that fast. So normal force equals 0. All right. And so our centripetal force really in this case is the gravitational force. It's the only thing acting in that direction. And so we know that Fc equals ms squared over r. All right, which means 2,500 equals ms squared over r. All right. Plugging in numbers here. 2,500 equals 250 times s squared divided by the radius, which in this case is 20. If you solve that, you should get that s equals 14.14 meters per second. Okay, so those problems should give you a pretty good indication of what is on the test. Test is very similar to this. So if you have any questions about it, make sure you come in and ask. And also, again, I recommend that you go back and look at the first video that I have over circular motion because I think that it will help you study for this. So check out both the videos.